Okay, so as I said, we're going to have a short video here, and I think I am just going to do the one story problem here. So this is a story problem here. It says the Game Commission introduces 100 deer into a newly acquired state game lands. The population N of the herd is modeled by N at T equals 20 times the quantity 5 plus 3T over 1 plus 0.04T. And then T is in the time in years. So first one is just kind of some arithmetic plug and chug, because it's just asking us for what the population when T is 5 and T is 10 years. And then the second question, though, is a little bit more, I wouldn't say difficult or involved, but it really starts talking about what is an actual meaning of these horizontal asymptotes. And these kinds of models here are very commonly developed for wildlife. And you might say, well, why would they do that? But especially if you just think of, if you've ever watched like Deadliest Catch or something like that, they have quotas on how much they're allowed to fish or harvest the crabs. And of course the reason being is that, well, if they harvest too many, then there's not going to be any to harvest in the future because the population can't replenish itself. So they're actually the Game Commission and other organizations actually closely monitor a lot of these wildlife populations, especially if it's something that we're harvesting for food, because we want to continue to be able to harvest it for food, so that they keep a close eye on these populations as much as possible, and then they develop. Now the models are a little bit more complex than this equation, but the same principle is the same. Alright, so let's go and dive into this one here. So again, part A is pretty straightforward here. We still need to do it, but we're just going to be plugging in here. So we have N at T is equal to 20 times 5 plus 3T over 1 plus 0.04T. And then we simply do the arithmetic here. So I'm going to look at what N at 5 is. So this would be 20 times 5 plus 3 times 5 over 1 plus 0.04 times 5. And then doing some arithmetic here, this would be 20 times 20. And if we have in the denominator here, 0.04 times 5 would be 0.2 plus 1 would be 1.2. Alright, so then again, finishing out the arithmetic, 20 times 20 divided by 1.2, and you get that this is 333.3 repeating. Now, really, we should talk about, since we're talking about a population, integer answers are the ones that make sense. In my opinion, technically, with integer answers, you should always round down, because if you're trying to be a little bit more precise, the 0.3, it's like, well, you don't have 0.3 of a deer. Some people might argue, like, well, a female deer is pregnant, and no, we're not going to be silly like that. We're going to make an answer that makes sense. And as I said, I typically always round down, regardless. So this would be 333 deer. And again, you would want to make sure to put units on there. And then, of course, the next thing is just doing this for N at 10. And then we have 20, 5 plus 3 times 10 over 1 plus 0.04 times 10. And again, just doing some of the arithmetic, we'd have 20 times 35 over, well, 10 times 0.04 is 0.4, so over 1.4. And so this would be 20 times 35 divided by 1.4, and I get 500 deer. So we can see that the population is increasing. Like you started with 100, after 5 years you have 333, after 10 years you have 500. Now, this is, if the deer just kept growing in population, then you'd have problems because there would probably be too many deer for this land area, and then you'd have issues with deer starving to death and other things like that. So we can see what is the population here. Well, the modeling to the top. So as I said, we wanted to get what this limiting population is. So part B here, the limiting population, and what that means is actually what does n at t do when t goes to infinity. So in other words, we're wanting to see if there's like a vertical, not vertical, see if there's a horizontal asymptote. So let's look at n at t. And let's see here, this would be 20 times 5 plus 3t over 1 plus 0.04t. Now I'm going to want to find the horizontal asymptotes of this. So I'm going to first just multiply my numerator out and write it in descending order. So this would be 60t plus 100 divided by 0.04t plus 1. And then if I look at my, again, my lead terms here, because I'm going to find my horizontal asymptotes, I've got a lead term of 60t and 0.04t. So my end behavior follows 60t over 0.04t, which is just, of course, reduces to 60 over 0.04. And then if you do 60 divided by 0.04, you get 1500. So what this tells me here is that the deer population is limited to 1500. And again, that's because as t keeps getting bigger and bigger, all we're going to do is approach that number 1500, and we're technically not even going to reach it. So even if we're talking about, like 100 years, the deer population wouldn't be more than 1500. Now, I will put one caveat in here, is typically these models are only for a set amount of time, and then they have to redevelop the models, and so on and so on. But the principle still follows, and these ideas of limiting horizontal asymptotes, limiting populations, or even not necessarily limiting populations, but we could talk about profit, because if you're setting the price of something, you might say, okay, well, there's a balancing point. If you lower your price, you might sell more items, but then you're taking in less revenue. If you increase your price, you probably sell less, but each item gives you more revenue. And so there's this trade-off. It's like, well, there's usually a limiting or a maximum profit that you can have. And you can look at the equations in order to get some of that here. All right. So as I said, this is the only example I'm going to do, and so it's a rather short video, and then we're going to move on to, in the next video, talking about graphs of rational functions.